Okay, people, on to example 3. Take a little break there for a second. Or at least I hope it's example 3. I mean, ain't that gonna happen? Maybe I might drop one. Probably not though. I'd like only if I find a mistake, which gosh, I hope not. But anyway, the point is, yes, let's do another example of this one-to-one onto all that jank. Don't be blurry. Don't be blurry. They'll go away. So this example is an interesting one. Probably the most interesting one we've done so far. Wait, let's use the whole whiteboard here. There we go. In this example, we want to let h be some function that goes from the natural numbers union 0, so all integers greater than or equal to 0, to the full set of the integers. And that's not going away, so I'm going to stop my share, then start it again. And it's like nothing happened. Nice. So we have, this is the domain of the code of our function. What is our actual function? So we're going to define our function to be h by h of n is going to equal, and it's going to be a piecewise function. And here's where things get interesting. So remember, a piecewise function, what h does to n depends on what n is. And so we're going to have 3 cases. We're going to have if 3 divides n, if 3 divides n minus 1, and otherwise. And notice these 2 cases are distinct because if 3 divides n, it will not divide n minus 1. By the fact we proved, like the next lowest multiple will be n minus 3 or n plus 3, right? So because n and n minus 1 are just 1 apart, if 3 divides n, 3 won't divide n minus 1. So these are 2 different, like these won't ever overlap. If 3 divides n, we want h of n to do, we want to output negative n over 3. If 3 divides n minus 1, we want h of n to output n minus 1 over 3. And then we want to output n otherwise. Okay, that makes sense to me. These are the piecewise things that our function does. So let's just do an example here. If we take like h of negative 5, for example. Well, let's see here. Notice that negative 5 minus 1, 3 does divide that. 3 divides negative 6. And so this is going to be negative 5. Oh, wait, I'm sorry. Wait. We can't even have negative 5 because we have natural numbers union 0 is our domain. So let's do 5. So as for 5, 3 does not divide n minus 1 is 4, 3 doesn't divide that. So the output is just the input, just 5. H of 6, though, well, 3 does divide 6. So this is going to be, actually, you know what, let's just go in order. So we start with h is 0. For h0, we get, well, 3 does divide 0, technically, because 3 times 0 equals 0. It's an integer multiple of 0, or 0 is an integer multiple of 3. So 3 divides 0, so that means it's going to output negative 0 over 3, which equals 0. Now, h of 1 is an equal sign, by the way. H of 1, what's that going to equal? Well, here 3 does not divide n, 3 does not divide 1, but 3 does divide n minus 1. 3 divides 1 minus 1, which equals 0. So that means we're in this case. In this case, the function outputs the input 1 minus 1 over 3, which is again 0. Now, h of 2 is an interesting case. So h of 2, oh, actually, no, it's not that. I'm sorry, it's not that interesting. H of 2, 3 does not divide n, and 3 does not divide n minus 1. So we go to the otherwise case. 3 does not divide 2, 3 does not divide 2 minus 1, which is 1. So we go to the otherwise case. So we output just n, which is 2. H of 3, here 3 divides n again, so in the top part. So we output negative the top, negative 1. H of 4, notice that h of 4, that 3 divides n minus 1, 3 divides 4 minus 1. So here we're going to output 4 minus 1 over 3, which is 1. And then h of 5 is again h5. 3 does not divide 5, 3 does not divide 5 minus 1. So in the otherwise case, we just output 5. Now we keep going. H of 6. 3 does divide 6. That means in this case, we're going to output -6 over 3, which is -2. H of 7, this is going to equal, if you plug 7 in to n here, or sorry, 3 does divide 7 minus 1. 3 divides 6. So that means we're in this case, so we get 7 minus 1 over 3, which is 2. Do you see the pattern here? What's happening is this number, this case and this case, keep generating all the positive and negatives of the integers in order. So you plug 0 in, you get 0, you get or -0 kind of, and 0. That's just 0. And then you skip over the otherwise case, and you get -1 and 1. You skip over the otherwise case, you get -2 and 2. And it's going to keep going like that. That's what happens here. The otherwise case is just kind of weird extra bits, which might not be good for a 1-to-1 or onto situation, or sorry, 1-to-1 situation, because immediately we have 2 outputs that go to, or 2 inputs that, or 2 distinct inputs that go to the same input. So that's no good. So immediately, actually, I'm going to point out, so we don't have to do it later. H naught But anyway, this is what the function does. Keep that in mind as we talk about it into the future. So, first of all, let's talk about well-defined. So this well-defined business. Remember, a function is well-defined if every input has exactly one output. And the only real case we could run into trouble here is with this overlap kind of business, right? Because if these two cases overlapped, well, then we would have 2 possible answers. Like if there was a number that was both divisible by 3 and n minus 1 was divisible by 3, if that number existed, well, then kind of both of these would be our output, and that's no good. We don't want that. So what we want to note that H is well defined is we want to say first, note that for each input in n union 0, 3 divided by n, and 3 divided by n minus 1, or I'll say, I'm sorry, for each input in here, negative n over 3 and n minus 1 over 3 give 1 output each. I'll say negative n over 3, n minus 1 over 3, and n give 1 output each. That's totally true. Why is that important? That's important because, you know, as long as these don't overlap, that means we're going to have 1 output. This gives 1 output, this gives 1 output, this gives 1 output. And so as long as these cases do not overlap, our function will consistently just give us 1 output. So further, for all n in our domain here, natural numbers union 0, 3 divides n we can't have 3 divides n and 3 divides n minus 1 simultaneously. If we did, then 3 would divide n minus n minus 1, which equals n minus n plus 1, which equals 1. And 3 does not divide 1. So there's like a little contradiction there. If 3 divided n and n minus 1 simultaneously, we'd find 3 divides 1, which is not the case. Hence, for each n in the domain, we either have 3 divides n or 3 divides n minus 1, or neither, but never more than one case. Thus, there is exactly, thus H gives exactly one output for each input of, for each input, yeah. So, therefore, H is well defined. So all we're saying here is that if you give me any integer in, it's gonna be one of these two, exactly one of these cases. Whichever case you go in, this will give me exactly one output. That's it. That means it's one. That means well defined. I wish I just said that. I.e. for each in the domain, in will satisfy one case, and each case gives one output. So H has one output. Really wish I just said that, honestly, but this is the long-winded reason of why all that's true. But this is the right to takeaway. Okay. Now, let's talk one-to-one, which we already talked about. One-to-one. Claim H is not one-to-one. Proof that H is not injective, for the word for one-to-one. So remember, to prove something is injective, right, we have to show that if there are any two things in the input that map to the same thing in the output, or is there any two things in the domain that map to the same thing in the codomain, the two things in the domain must have been the same. If f of A equals f of B, A must equal. But to disprove that, to prove the bijection, to prove the negation, to prove that H is not injective, all we have to do is show that there exists two inputs in the domain that map to the same output in the codomain. And we already saw what those were. Consider A equals, what do we have? That's a good example. Consider A equals, I believe it was 7, yes. And B equals 2. Note, since 3 divides 6, which equals 7 minus 1, H of 7 would be, in this case, would equal 7 minus 1 over 3, which equals 6 over 3, which equals 2. Further, since 3 does not divide 2, and 3 does not divide 1, which equals 2 minus 1, we're not in this case, we're in the otherwise case, H of 2 equals 2. Therefore, there exists distinct inputs, 7 and 2, that map to the same output under H, that being 2. Thus, H is not one-to-one. So we circled them before, and now this is the formal proof that H is not one-to-one. So to prove one-to-one, assume that f of A equals f of B and show A must equal B. To disprove, just find A and B. that are different from each other, such that f of a equals f of b, or such that h of a equals h of b. You know what I mean? That map to the same thing. All right. Now, last we have onto. That's really the interesting one here. So onto is the interesting one. All right. So to prove a function, so first of all, do you think this function's onto? I'm going to say yes. Because of that kind of table thing we made in the very beginning here, we showed that we had h of 0 goes to 0, h of 1 goes to 1, h of 4 goes to negative, or sorry, h of 0 goes to 0, h of 1 goes to 0, h of 3 goes to negative 1, h of 4 goes to 1, h of 6 goes to negative 2, h of 7 goes to 2, h of 9 goes to negative 3, h of 10 goes to 3, on like that. We're actually going to ping pong around, it seems, and hit every single integer in the codomain. How do we prove it? And here's how we prove it. I'll say at the beginning, note from our observations, it seems that well, it's not like from observations, it's just from this. From this and our observations, we totally gather that in the case that plugging in the multiples of 3 will get us will get us 0, -1, -2, -3, etc. And plugging in numbers 1 more than a multiple of 3 gets the positives. 0, 1, 2, 3. Not that 0 is positive, you know what I mean, etc. On and on and on like that. That seems to be what's happening here, right? And we can see that, right? If we plug in h of 0, we get 0 divided by 3, which is 0. H of 3, at 3 divides 3, we get negative 3 over 3, which gives us -1. Plugging in 6, the next multiple of 3, we get -6 over 3, which gives us -2. Plugging in 9, the next multiple of 3, we get -9 over 3, which gets us -3. This goes on and on like that. Now, if we plug in we consistently plug in the numbers 1 more than a multiple of 3, h of 1, now we're in this case. Every number 1 more than a multiple of 3, you can subtract 1 divided by 3, so we're in this case. So h of 1, for example, 1 minus 1 is 0, 3 divides 0, so we're in this case, so we get 1 minus 1 over 3, which is 0. H of 4 gets us 4 minus 1 over 3, we're still in this case, which is 3 over 3, which equals 1. H of 7 gets us 7 minus 1 over 3, which is 6 over 3, which is 2. H of 10 equals 10 minus 1 over 3, which is 9 over 3, which equals 3. So you see these numbers goes by 3, the multiples of 3 are producing the negatives, and these numbers 1 more than multiple of 3 are producing the positives. So here's how my onto proof is going to go. Proof that H is onto. So the proof goes like this. Again, remember, want to show for all M in our codomain Z, there exists an end, the natural number union 0, such that H of n equals n. That's what we're trying to prove. So let M be any arbitrary / particular element of Z. Note M is either greater than or equal to 0, or sorry, M is either less than or equal to 0, or M is greater than 0. So you have two cases here. Case 1, M is less than or equal to 0. Now, since less than or equal to 0, I want to generate it with these multiples of 3. So I'm going to let n be the mth multiple of 3, and I think when I plug it in, I should recreate m, proving we can hit m. So let's go ahead and let n equal 3 times the absolute value of n. Absolute value because m is negative, so I want the mth negative number, but m like the positive version of m. You see what I'm saying? Like if m was 2, I want n to be 3 times 2, which gets me 6. When I plug in 6, I get negative 2. Or sorry, if n was negative 2, I want n to be equal 3 times 2, which equals 6, which gets us negative 2. So I want to take like the positive version of this, that multiple of 3, that when you plug in should recreate your m. So let n equal m 3 times m. Then note, since m is absolute value of n is certainly in Z, 3 divides n. Thus, h of n, or in this case for 3 divides n, will get us negative n over 3, which is negative 3 times absolute value of n over 3. These cancel out, and this gets you negative absolute value of n, which equals m. And this is true since m is negative. Right? If you take any negative number, like say negative 5 is going to equal the negative of its positive version, right? Obviously. So this means that so for n less than or equal to 0, we could find an n. Oh, and we should note one last thing. Note, since absolute value of anything is greater than or equal to 0, 3 times n is in natural numbers. I.e., there exists an n, the natural numbers union 0, such that h of n equals m. So if n is less than or equal to 0, we can use like the multiples of 3 to get us exactly what we want. Now let's move down here. Let's get below the glare. All right. Now let's check out what happens if m is greater than 0. For numbers greater than 0, we really want to use the one more than a multiple of 3s. The 1s, 4s, 7s, 10s. Those would be 2. Recreate our m here. Specifically, it looks like h of 4 creates 1. Or 1's created by 4, 2's created by 7, 3's created by 10. So it looks like the number we actually want to use here is whatever this number is, multiplied by 3 plus 1. Looks like if you plug that into h, we'll get that number back. So if m is greater than 0, then let n equal 3m plus 1. Note 3m plus 1 is definitely in n union 0, the domain. Then, since 3 must divide 3m, which of course equals, since n divides, 3 divides n minus 1, which it does because this is going to equal 3m plus 1 minus 1, which equals 3m. Since 3 divides m minus 1, we have h of h of n is going to equal, we're in this case now, it's going to equal n minus 1 over 3. n minus 1 over 3, which equals 3m plus 1 minus 1 over 3. Plus 1 minus 1 cancel out, so we get 3m over 3, which just equals m. Aha! So in either case, we can construct an n in the domain that we can specifically plug in to get n back. So in either case, there exists an n in the domain such that h of mn equals m. Therefore, h is onto. So the point is, this is complicated, but it's exactly the same as every other onto proof. All we have to do is go through and show that for any single m you pick in the codomain, I can find an in the domain that when I plug into h will hit that m. And then we're done. So our h function here was complicated. It's a very interesting function. It was onto, but it was not one-to-one, but it was well defined. So that's why it's a function. But anyway, the really interesting thing about it was that h went from the natural numbers including 0 to z, which is odd because the natural numbers including 0 is a subset of z. In a certain sense, it feels like a smaller subset, right? Because it says this doesn't include any of the negative numbers. So it's weird that we were able to hit all of the z's, right? But actually not really. We kind of did a classic technique of kind of alternating where like one natural number went positive, one went negative, one went positive, one went negative, one went positive, one went negative. Kind of classic technique. But the point is, it shouldn't be that surprising because it's going to turn out that we can actually form a bijection between here and here. And once you can make a bijection between two things, that means they really kind of have the same size. So even though n and z feel like z is bigger than n, it really isn't. There's really, in a certain sense, the same number of elements. Really weird to think about, but interestingly true. So yeah, that's that example.